So my name is James Powell. I'm giving the third unofficial keynote of PyData London. I'm really excited to be here. I think the conference has turned out to be fantastic so far. I'd like to introduce myself briefly, then we'll jump into generators. I know that the other talk, so this talk is listed as advanced, and the other talk was listed as novice. The material that I have prepared for you actually goes from novice to advanced, so I may spend a little bit of time towards the novice side just to see if I can cover as much as possible. So, as Ian said, these are all the meetup groups in the world. And if we scroll down, we can see there's a lot of really big ones in Silicon Valley that are general interest. And if we scroll down to number 5 here, we see the first Python-specific meetup group on this page, NYC Python, 4,509 members. This is our meetup group, and you see there's my dopey photo in there. I think I'm actually wearing this suit in that photo. It is something that I am probably one of the things I'm most proud of that I do in the community, which is run this meetup group. You can see our next event is actually at Pivotal. I'll be giving a CPython workshop, very similar to the talk that I gave on Friday. This is just an amazing group of people. The amount of energy, the amount of excitement towards Python, towards big data, towards web programming is just absolutely, it impresses me every single time. Additionally, I am running a conference in New York City on the 14th of March called For Python Quants. A couple of speakers from today will be there. It is a conference that is a little bit more specifically targeting the intersection of big data, finance, and Python. So a couple of speakers, I'll be speaking. We have somebody from Quantopian. Dr. Hilpish will be speaking about derivative analytics. And the keynote will be given by Kirat Singh, who has twice over developed the 2 largest Python systems in industry that nobody seems to know about, one at JP Morgan and one at Bank of America. So some very, very exciting talks. Also, I have a blog here. I haven't updated in a very long time, but if you want to go into any wild, wacky coding, I have some. So the domain that I got for it was don'tusethiscode.com, and I put the blog on seriously.don'tusethiscode.com. I thought that was great. One of the other things that I do is I help, this one's the one I want to go first. So I help run the PyData conference series. I'm one of the co-organizers. So what that allows me to do is it allows me to tweet and then to retweet myself from the stage. So I think if I go to this one here, I'll actually be able to retweet myself immediately. And it is said that power corrupts, and that absolute power corrupts absolutely. So I don't know if I should tweet this or not. I thought that would be quite humorous. But you can see that when you have access to the Twitter feed for PyData, you can do quite a bit of damage. So I don't know, maybe I'll just delete it after this talk. Tweet. So this is one of the things I do. So let's get started with generators. So just as a show of hands in the negative, who looks at this piece of code and doesn't know what it does? So who's clueless when they see what this does? Just so that I can calibrate where I want to go. So everybody knows what this does. Great. Who looks at this piece of code and doesn't know what it does? OK, so everybody knows what a generator is. Fantastic. Who looks at this piece of code and has no idea what's going on? OK, so coroutines, people are a little bit soft on. Who looks at this piece of code and doesn't know what's going on? So generator expressions. And then finally, who looks at this piece of code and doesn't know what's going on? So don't lie, because nobody knows what's going on in this piece of code. This is wild, wild stuff. OK, great. So the notes for this are in an IPython notebook. It'll be posted along with the other slides. I have this laid out. I'm going to spend a little bit more time towards the beginning of these notes, just so that I can cover the introductory details of what a generator is. So again, here are some of my details. You can email me at james@don'tusethiscode.com. You can follow me on Twitter at don'tusethiscode or Python Quants. You can read my blog, seriously.don'tusethiscode.com, or you can attend NYC Python or the conference that's being run on the 14th of March. So I like to look at generators and functions from a formal perspective. And by formal perspective, I mean the form of them. Because you can see in the previous example that my generator and my function look very similar. And the only difference is, from first glance, the only difference is where there was a return, there's now a yield. So starting with that, this is just a very typical function. And throughout the notes, throughout this first section, this is just about the standard function that I'll use. All it does is it returns 2 values, x plus 1 and x plus 2. And you can see that I test it, and you can see the example usage of it. I call the function with this parentheses, and it returns an answer. Nothing too fancy. And then we can see that a generator, formally, is just the same thing as this function, except instead of a return statement, I have a yield statement. And in the example usage, instead of calling it with parentheses. I call it with parentheses to instantiate the generator instance, and then I iterate through it in order to get the values. So in the first case, I'm getting the values immediately when I call it with these parentheses. And in the second case, I have to iterate through the resultant object in order to get the actual result. And you can see that a generator expression is very similar to a generator, except instead of having this extra step of instantiating the expression, we essentially inline the generator instance. So nothing too fancy here. I think, though, if we step one level higher, we can see that in Python there are these fundamental protocols. So I view Python as a collection of ad hoc fundamental protocols, the two most fundamental of which are callability and iterability. So let's talk about iterability, or let's talk about callability first, actually. So callables in Python are just a generalization of function. And we know that there are these things that sit in our code, and we can put parentheses after them, and a result comes out. One example of them is a function. But another example is a class. You put parentheses after the name of the class, and you get a class instance. There's also generator objects themselves. You put parentheses after that, and you get a generator instance. There's also C functions, which under the hood look very, very different than regular Python functions. But you put parentheses after that, and you get a result. And we can see that part of what Python allows us to do is it allows us to look very abstractly at what's going on. So in this case, we have a callable, and it's just some random object, and it implements underscore call underscore and gives a result. And there's nothing too fancy here, and we could do this in order to implement any sort of abstract behavior that we want under this protocol of callability. Nothing very interesting at all. Similarly, iterability is one of these abstract protocols that we have. So there are a lot of different things in Python that we can iterate over. We can iterate over lists, but in the same sense, we can implement init, iter, and next, and we can create a custom iterable object. And all it is an object that has some protocol, some code, that we interact with in a very defined fashion. And we have a usage site right here. And it desugars into the resulting of a value where we iterate through a set of computations. Now, this is to motivate what a generator really is. Because if you look in the CPython code itself, you'll see that both functions and generators share an enormous amount of code. In fact, when you pull out a value from a generator, you really go through the same eval frame x code that you would if you call a function. And behind the scenes, actually, a generator is really just a function with a special flag set, so that the first time you call it, you get a code object paired with a frame object that just kind of lingers around. Or to put it another way, in a function, in the C code, when you hit return, you clean up all of the local state that you've generated, and you return a value. In a generator, when you hit a yield statement, you actually leave. You literally leave everything around, and then for you to re-invoke it. And if you look at eval frame x, you'll actually see quite literally this is the case. When you return, you jump to the bottom of the function. When you yield, you jump past the cleanup and continue. And so the code is actually very simple in this case. What a generator really is just some iteration with some notion of state. And this can be related to things like delayed computations, to laziness. But in its essence, all it is something that you can iterate over in this formal mode of for x and xs. And it remembers where it was. And so here we have an example of some abstract iterable that just implements this protocol. We have the ability to get the next element, and we know where we last were. And if we generalize this to computations, we can think that a generator is just iterating over something where the things we're iterating over are computations, and our state is what was the last computation that we actually computed. So coroutines. And what are coroutines? Coroutines, if you go to Wikipedia, you can see that Wikipedia says that a coroutine is a generalization of a subroutine. And what they mean is this. In our first formal example, we saw that a function has one entry point and essentially one exit point. You call a function with some input parameters, some code runs, and it returns. And it eagerly gives you the result of some computation. So f of x, in the first example, gives you x plus 1 and x plus 2. A coroutine is a generalization of this where you have multiple entry and multiple exit points. Namely, you can run a block of executed code, and it pauses. And you're able to re-enter that executed code and return some more values and leave that state intact. Re-enter that, return some more values, and leave that state intact. And so in Python, very formally, a coroutine gives you, a coroutine is implemented by the addition of 3 additional methods, namely throw, send, and close. So I'll go over this very briefly, and then we can get into the meat of why you'd want to do this. So here we have our very standard generator example. We take one input, x, and we first yield x plus 1, and then we yield x plus 2. In order to get these values out, we have to iterate. So unlike the function where the code runs to completion on invocation, the generator only returns values as you ask for them. And in order to make this a coroutine, we just see that there's a next method. So in Python 2, it's called next. In Python 3, it's called _next. And all this is our way to interact with this protocol of getting the next computation or the next value out. So just like in the for loop, we can take our for loop and we can desugar it into a while loop that just calls next until we've exhausted the computations. Next isn't anything terribly interesting, and it's part of the basic generator protocol. However, throw, close, and send are what we're talking about when we talk about coroutines. So you can think that if our generator is yielding chunks of a computation, at some point we may want to raise an exception. Because in regular code, we have some desire to raise a computation. And throw is just one way that we can raise an exception inside of this computation. It's not terribly useful, and you don't see it used that often outside of large libraries that use generators quite extensively, like Twisted or something like that. It's not something that we run into very often. Similarly, close is our way to take a suspended computation and close it, to say, clean up, you're done, we're never going to get another computation out. The meat of this all is, and I don't know why I put it last, but the meat of this all is send. So in a function, you have one chance to get input in, and you have one chance to get output out. And you may have, in the actual coding, many return statements. But if you think about it, input comes in, and you return at one of those statements, and the computation is completed. In a generator, what you can do is you can put input in when you invoke the generator. And then at each stage, you can add additional inputs in and get additional outputs out. And you can actually relate those partial inputs to the partial outputs. So here we have a generator that's very simple. All it does is it takes an input value, and it yields that input value plus 1. And then it also yields the state of this internal variable, y. And then it takes in some additional input, stores it to y, and then runs again. So if we look at the running of this, formatting here is not that great, but we put in 10 first, and we grab the next value. So we have 11 and none, because y was set to none. And then in the next step, we can actually send a value back into the generator. And inside this computation here, we can make use of that value. So you can see gsend, abc, and we get 12, x plus 2, and abc. And what we could do here is we could actually do something like that. And we could actually perform some additional computation on some additional input. So in this sense, a coroutine is merely a function where you have the ability to suspend it and then add more inputs. You have a generalization of a function or a subroutine which only takes input once and returns output once. Now there's one note, and these are very important to what happens in the rest of the slides, which is pumping and priming. And this is kind of a wart of how generators are expressed in Python. If you look at a large library that uses generators extensively, something like Twisted, you'll see somewhere along the line somebody's written a decorator called pump or prime. There are a lot of different names, but it has to do with when you can get inputs into the generator. So here's our very simple generator, and you can see that we've tried to put a value into it. And we get this nasty and very strange error called can't send none value to a just started generator. The problem is this. When we want to put input into the generator, we have the ability to start this generator instance with some value in the formal parameters at the top, generator x, right here. And then as we want to add additional inputs in, we have to think, when are we actually able to inject them into the generator? We can't do it. What happens in this code is we'll run all the bytecodes from here down to the first yield, and it will result in this value. There's no way for us to put a value into the generator before this first yield statement. And as a consequence, you can't send a value into a generator or send a value into a coroutine before that first yield statement. And it's very hard to really wrap your head around this, and it results in weird errors like this error below. But just as a note, whenever you're looking at a large code base that uses generators or uses coroutines, you'll probably see something called pump or prime. And it's trying to avoid this ugliness of syntax where getting that first input into the coroutine is just not possible given the syntax and the form of the generators that we have. Now I want to give a little aside about itertools. This is out of my 23 most favorite libraries in Python, this is probably number 2. Actually people believe that I have 23 most favorite libraries in Python. As a side note, I'll tell you that I don't have any cards left, but I have some business cards for NYC Python. And on the back, I put different import statements. I went through all the code that I wrote in my little Scratch folder, and I put all the import statements that I used most commonly. From this, import this, from C-types, import from C-types, import PyObject, from itertools, import chain, and I found all my most favorite imports. I had 6 of these. And I sent this to a friend of mine who is on the core organizers list but wasn't very technical. And I said, what did you think of these slides? And he said, what's that weird program code on the back? And I said, actually, each one of these has an exciting story to go behind it. And I wrote out a very long email with a 10-minute story for each one of those inputs. And his response was, I wish there existed in some language a word that meant, I immediately regret asking this question. So I'll tell you about itertools, which is one of my favorite libraries, because it's very relevant to generators, and it's very relevant to the use of generators in Python. One reason that I think generators, among all the features in Python, deserves a talk by itself is that if you look at the transition from Python 2 to Python 3, you can see that the focus on this fundamental protocol of iterability is one of the distinguishing factors of Python 3. Namely, in a very superficial level, things like map and filter have been turned into these lazy map, what in Python 2 is called IMAP or iFilter. And you can see that this focus of iterability as a fundamental protocol has taken center stage in Python 3. And itertools is one of our most useful libraries for interacting with iterables, whether they be generators or just classical iterables. So itertools is a collection of generalizations, it's a collection of helpers, it's a collection of algorithms. And you can see throughout these notes and throughout my code, it is one of the most useful libraries that I have. And it allows us to solve a lot of problems in a very robust and very generic fashion. So when I talk about generalizations, one of the examples is iSlice. So we know that standard lists can be sliced. We have this syntax to get elements from 1 to 5, not including number 5 out of a list. And here we have a formulation of a Fibonacci sequence as a generator. And we have the ability to slice through this as well. We can't use this bracket 1:5 syntax to slice into it, but itertools gives us something called iSlice. And iSlice is a way that we can slice into something without having to know what it is. So iSlice could allow us to slice through a list, a dictionary, a tuple, or a generator. It's a generalization of a very standard mechanism. And similarly, in Python 2, we have izip, imap, ifilter. We have these generalizations of ways to look at these iterables without having to know anything about their internal details, their implementation details. Similarly, itertools contains a lot of helpers. So we know that we can append lists. And I'm sure that almost all of you have at some point run into some code that added one list to another list. And it turns out that when people were calling this code, or somewhere in the function it adds one list to another list, and when people were calling the function that does this, they accidentally passed in a tuple. And they got a really nasty error saying you can't add a list to a tuple. I know I've run into this a couple of times. And you could think that chaining two things together is a very natural thing. It doesn't matter what A is, it doesn't matter what B is. You may just want to chain them together without having to know that this is a list and this is a tuple. And chain is one of these helpers. It is a way that we can take any sort of abstract iterable and concatenate them together without having to know anything about how they work internally. All chain does is it gives you a wrapped iterable, and it goes through all the values of the first one and then all the values of the next one. It tends to be very, very, very useful. It is probably my third most favorite function in Python, chain.from iterable. And so you can see that similarly there's T, there's repeat, there's cycle. There's a lot of these very nice helpers. Itertools is a fantastic library. It's one of the best parts of the standard library. And similarly, in the standard library, we have these algorithms. So here we have an infinite sequence of Fibonacci numbers. So this is a generator, and it'll just continuously generate numbers from the Fibonacci sequence. And that's not terribly useful for us, because if we try and stick it into a list, we'll run out of memory very quickly. But what we might want to do is we might want to take certain elements of them. And itertools includes a function called takewhile. And takewhile allows us to give it a predicate and just take elements from this iterable until this predicate is no longer met. So here we take all the elements from the Fibonacci sequence where that element is less than 50. Similarly, itertools includes dropwhile. It includes product, combinations, permutations, all of these ways that we can take our sequences and combine them and perform different, very standard permutations on them. So, given that, and given our knowledge of what a generator very roughly is, there's a question of why we want to use it. What's the purpose? What's the goal behind this? Why would we want to apply this sophistication to our programs? And I think that this can be answered in two parts. And the first answer to this question I find is usually something about efficiency. And I don't think that it's the most compelling answer, but it is the most common answer. So let's think for a second about what a function is. A function eagerly computes some sequence of computations. So it has one entry point and one exit point, and from entry to exit, it does the entire computation. And a generator instead gives you the ability to segment that computation, to demarcate that computation into chunks. And it'll do each one of these pieces only as you ask for that computation. So very naturally, I think what we can get from this is an idea that generators give us memory efficiency in this sense. This guy, pairwise, is something that pops up in my code all the time. Namely, for some reason, I have some set of data in a stream, and I want to look at windowed pairs of it. So if I had numbers from 1 to 10, I'd want to look at 1, 2, 2, 3, 3, 4, and so on. I want to be able to compare the current piece of data to the next piece of data or to the previous piece of data. A very simple example of this is some sort of windowed average. If I wanted to take the average of every 3 elements from a stream, that would just be pairwise with a size of 3. Here I have it implemented in our very standard fashion as a function. And you can see that it creates a temporary variable called pairings, and it will take the first element and the second element and stick it into pairings, and the second element and the third element, and so forth and so on. And if I run this on a list of numbers from 0 to 9, this is the output. And it's pretty straightforward. But you can think, what if I run it on elements from 0 to 1 million? This function, by virtue of having to do the entire computation at once, is probably going to run out of memory or probably stress the memory that I have available. And in the case that I'm doing something like a windowed average, I don't need the entire computation. I only need each one of the windows at any one point in time. Generators give us the ability to look at only the part of the computation that we need immediately. So here I have pairwise rewritten as a generator. And you can see that the code's a lot simpler. I no longer have to deal with this temporary variable. It's actually a little bit shorter and a little bit clearer. And here, it still gives me the elements from 0 to 9 paired up. But if I were to do this and actually try and print pairwise of x range 1 million, it'll give me a result. And the result it'll give me is this deferred computation here. And as I want each of these elements, I can pull them out, I can process them, but I won't have to allocate memory equal to the entire size of this list. This is something that's very, very powerful. It allows us to construct our computation as a set of independent units that work on streams, where each one of them doesn't have to run to completion, but can iteratively look at one part of the computation and then pass it down the stream. Additionally, and this is one reason to look at itertools first, is itertools allows us to create things like n-wise or pairwise very nicely, very succinctly, very robustly, and very quickly. So in later parts of these notes, I'll be using this formulation of n-wise, which is just a combination of pieces from itertools. It looks really scary, but it's actually very simple. This is something that I can type by memory because I've typed it so many times. Essentially, all we do is we take the stream, we copy it 3 times, we enumerate each one of those copies, and then we stagger them. So we take from 0 to 9, and we stagger the next one from 1 to 9, and the next one from 2 to 9, and then across, we zip them together. So this is just a generalization of this pairwise. And you can see that we can write it as a formulation using these fundamental building blocks from itertools very, very tersely and very efficiently. So we can see very easily why we want to motivate the use of generators. by virtue of not having to complete the entire computation, we can look at only subsets of the computation, and those subsets only require memory equal to the window that we need. So in the case of, for example, pairwise, we only need memory storage for the two values that we're looking at right now. And if this pairwise were being used for a rolling average, we only need memory equal to the number of elements that we have in that window, as opposed to needing memory for the entire sequence. So we have great gains memory-wise. There's a question of time efficiency. And this is a very tricky one to answer. So I'll give you one example of something that I find to be fairly unconvincing, but still, nevertheless, is somewhat interesting. Here I have some C++ code that I wrote. Now, I haven't written C++ in a very long time, so this isn't very good C++ code. But all it does is it implements this pairwise with a window of 3. So for the numbers from 0 to 9, it'll give us 0, 1, 2, 1, 2, 3, 2, 3, 4, and so on. And I've written the same thing in Python. And you can see that this is actually a lot less code. I wrote it in the same formulation as the itertools version, where I'm just combining these big building blocks. And this is written fairly naively. So I haven't put any attention into optimization. And when I run this, so I'll show you if I run this. You can see that's what happens when I run it. They both give the same result. So from 1 to 10, I get 1, 2, 3, 2, 3, 4. That's all it does. And what's interesting is when I time this. So here at the top, we have our C++ version being timed. And here in the bottom, we have our Python version being timed. And you can see the times are actually fairly close to each other. So we have 3.2 seconds total at the top and 3.6 seconds total at the bottom. It is fairly rare for us to write naive Python code that runs within an order of magnitude of C++ code. It's fairly rare to us. Now, the reason that it works in this case is because this is probably I/O bound. But in general, there is something to be said about generators as a tool for time efficiency. It is, I don't personally like this example that much. People seem to really like comparisons between C++ and Python. And I think that this example, that comparing the two directly does, in some cases, miss the point. But it does show us that there is something very interesting happening here. However, we can see that the question of memory efficiency or of time efficiency is one that is not so easily answered. Here I have a primality, just a very simple primality checking written as a generator expression. And all I'm doing is trial division. And when I run it, you can see that it's 2.2 microseconds per loop. And then here I've written it in what you might consider kind of dumb Python format. And you can see it's 1.3 microseconds per loop. And what this tells us is that the process of creating or instantiating a generator instance actually overwhelms the time put into the computation. And so this is not really always the most efficient mechanism by which to solve our code. But I think the most important thing about generators are these structural considerations, namely modeling. So the first part is stream data processing and pipeline flow. You can see that since each one of these generators is building blocks, it only works on one tiny piece of data, we can very nicely create a program that composes these high-level building blocks as just like if any of you have been in a band, you have your guitar connected to your amplifier, connected to the distortion, connected to this, connected to that, and each one of those pieces along the line processes only a slight piece of data and then sends it down the pipeline. And we can do this very nicely and very naturally using generators. But more importantly, I find that generators kind of free us from a lot of presumptions that we have, namely presumptions about return type. So here's our Fibonacci example, and this Fibonacci gives us the Fibonacci sequences up to some number in a list. And you can see that if I didn't want a list, but I wanted a set or a tuple, it would take me some time I would need additional memory equal to the list and the set that I'm constructing that have to be in memory at the same time. And I have to put some time into converting them. Whereas if I write this as a generator, I've made no presumption about the return type that the user wants. And as a consequence, I do save some time. And I save a lot of memory because I don't have to keep both of these structures in memory at once. So I've freed myself from having to presume how the user is going to use my code. Similarly, I can free myself, and this is very important, I can free myself from presumption about return values. So one thing about the Fibonacci sequence is that when I want to write it as a function, I have to think, do I want all the Fibonacci numbers up to but not greater than some number n, or do I want the first n Fibonacci numbers? And this is something that I have to bake into the way that I write this problem. And if I wanted both, if I wanted my function to be able to give the first 5 Fibonacci numbers or the first Fibonacci numbers not greater than 5, I would have to add in a lot of really crazy modalities. Whereas in the generator formulation, I can use these pieces from iter tools in order to write my generator with no presumption about how you're going to use it, and then use these building blocks from iter tools to then pull out the values that I want. So instead of having to write 2 versions of it, I can write 1 version of it that just gives an infinite stream, and I can slice and dice that infinite stream as I desire using take while or even islice. Additionally, I can remove from consideration some presumption about how the values will be used. So here I have this same example with a sleep put into it. And you can see if I only want the first value, in the functional example, I still have to incur the sleep, because I have to incur the entire computation. Whereas in the second example, if I only want the first value, I'll get the first value, and I don't have to incur the sleep because I don't want any values beyond the first. And this is something that's very important, because in a lot of cases, I've seen modelings of trading books, and they contain millions and millions of deals. And you want to load up only some subset of the deals in order to produce some analysis. And in one case, this was written as a function, and so it would load all the deals and run out of memory. And I couldn't even load the 5 deals that I wanted out of the book of hundreds of thousands of them, because it tried to load them all up eagerly at once and ran out of memory. Whereas in the generator example, I make no presumption about what you want to use. I say, I'm just going to provide you an infinite sequence of these, or I'm going to provide you all of them, and you get to choose from the outset how you want to slice and dice this data, how you want to pull, which of the computations you want to perform. So I don't have time to go into this, but this is one example of where this can be used very nicely in practice. So business date calculations. This is something that every large system ends up writing itself, which is some mechanism by which to calculate what's today plus 2 business days according to some holiday calendar. And this holiday calendar is usually stored in some SQL database. And when you write this as, and people write this every time I've seen this written, it's been written in some non-closed format with a big while loop, and it ended up being a whole mess. And there was a presumption about how you wanted to use these business days. So if you wanted to get the first 5 business days in some particular fashion, or if you wanted to get the next 5 business days, you may be incurring a lot of redundant calculations. So here's an example of one way that you can formulate this as an infinite sequence of holidays or an infinite sequence of business days, and use the formulations that generators give you in order to very nicely from the outside slice and dice and determine which of these computations or which costs of computations you want to incur. Additionally, knobs, buttons, and modalities. So here's a really interesting example, which is a lot of functions. We've seen in large libraries, a lot of functions start to accrue all these knobs and these modalities and these little pieces on the end. So they end up getting these very long parameter lists. And what generators allow you to do is to encode some of these problems very, very nicely, very succinctly, and very generically. So here's an example of one where I've implemented, so here we have this nasty little pumped thing, where I've implemented a coroutine called predicate that just takes values out of something until some predicate is hit. And I've implemented this guy greedy, which is just a combination of pieces from iter tools, which implements a greedy algorithm. And if you think about it, the greedy algorithm is just you have some trace of information, and you pull as many of these out of here until you hit some predicate, and then you move on to the next piece of information and pull them. And we can actually use this to solve 2 very different problems without changing that fundamental library code. The first problem we can solve is change calculation. So here you have change drawers with infinite numbers of denominations for each one of the denominations and currency that you have, and you just pull them until you hit some predicate which says the next coin that you take would take you over the number, you go to the next drawer, and so forth and so on. Similarly, in the user code, so notice there's no additional modes or knobs that I had to add to the library code. Only the user code actually drives the use of this. And here I have another example where I'm solving a very different problem, which is Roman numerals to, or sorry, Western dates to Roman numeral dates, using the exact same piece of code where I've just changed, or I've just fed into it a different set of data, which is a mapping between Roman numerals and Arabic numerals. So very, very interesting. So I want to talk about the showcase. I don't have a lot of time, but I run this meetup group, and one of the things that we do is we like to give away a lot of prizes, because we get a lot of books from Pearson and O'Reilly. And I remember when I was young that I used to watch The Price is Right. And The Price is Right is a show that exists throughout the world. This is the American Price is Right. There's actually a Price is Right in Great Britain as well that's been on the air since the 80s. And it turns out I speak Chinese, and it turns out there's also a Chinese Price is Right as well. So The Price is Right is probably one of the most popular game shows in the world. And there's one game called the Showcase Showdown, which is a giant wheel and they spin it. And this determines whether you get to show up for the showdown later on in the show. And so we wanted to write some code to give away live some of these prizes. And this is something that hopefully we'll be able to do in the afternoon today. And what I wanted to do is I wanted to write a wheel. I wanted to count people off, and I wanted the numbers to show up on the screen. I wanted them to slow down, because when you jump up and pull that wheel, it'll slow down as it gets towards the end and build up the tension. So I wanted to do that. And I did this by implementing this just with some pieces of iter tools, putting sleeps to slow things down. But then I thought, I want to make this a little wilder, because sometimes with The Price is Right, the wheel will go down to $1, which if you get twice, you get $25,000. And the little flipper will push it back, and the wheel will go backwards. And I thought, how could I model a wheel that could also go backwards? And the first thing that I reached for was object orientation. But you could think that if I were to write this in an object-oriented fashion, it would end up being really, it would seem very naturalistic, but it would end up being kind of weird. I'd have like a spin method, and I'd have a this method and a that method. How can I use generators to model this? And how can I use it to model it more simply? Well, I could create a generator called wheel that very abstractly takes some input and just runs over the data. So if I give it a list of numbers from 1 to 3, it'll do 1, 2, 3, 1, 2, 3, 1, 2, 3 ad infinitum. And I can give it a direction as well, so I can tell it 1, 2, 3, and then go backwards. But the interesting thing about this, because it's so simple, is that I can test this very easily, far more easily than I could test the object-oriented solution. Because the object-orientation solution would have embedded in it all of this state and all these modalities, whereas this is lacking in a lot of modalities and has no state. So I could just test, in a very simple test, wheel of 1, 2, 3, does it give me the numbers resulting? I have that as a test later down here. You can see I can test it. I can just make sure that the numbers come out in the direction that if I do backwards, they come out backwards, and so forth and so on. Similarly, I can create another generator called spin. And all this does is it takes my wheel and it just spins it, given some function saying how fast it needs to spin. And so here, I've given a transition function that says, OK, it slows down according to this rate. And I can also test that velocity function. And this just gives me the velocities at which it should spin. So unlike the object-oriented fashion, where I'd have to test it in some weird fashion, where I'd have to set up some unit tests, and I have to mock this and mock that, here I just have some function that gives me the velocities. And all I have to do is make sure that for the wheel to stop, it goes from some high speed down to some low speed and stops. And you can see here, this one actually goes to a negative speed, so it actually will go backwards. And putting these together, I end up with something that looks like this. It doesn't show up very nicely in IPython Notebook, because IPython Notebook won't show each one of the initial ones. But in the end, I end up with a very interesting solution for a spinning wheel that's built of very fundamental building blocks that I could reuse throughout my code that make no presumptions about how they're being used, where it's not the library author that's dictating things, but the user of the code that is able to make use of this as they see fit, where I can add in an enormous number of ways to use this, an enormous ability from the outside to control this with very little code. So I want to show you this guy in practice. You can see we may do this later today. Oop, this one here. So here we go. And we did this in n curses, so it'll actually slow down. I don't know if it'll go backwards, but you can see it'll spin, and as time goes on, it'll actually slow down. And your heart will start pumping to see, are you the one who's actually going to win the book? And sometimes, I love it when it goes backwards, because somebody's like, yeah, I got the book. And then it goes up to the next name, and they're very disappointed. And I love to see the look of disappointment on people's faces. So, what this tells us is that generators are not just some feature that's added in. They're not just some feature that we can look, like decorators we can look at and we can say they're very interesting, but they're just a feature that was added in that allows us to remove some boilerplate. Generators are a way that we can fundamentally reconceptualize how we write our code. It allows us to encode lazy computations, and it allows us to very fundamentally change how our functions look, to be able to write some very abstract, very reusable, very non-presumptuous blocks of code. Code where, for example, in this wheel, you could add in any velocity function, any transition function, and you could have the wheel move in any direction, however you choose. And all of that is controllable from the outside. It's not you come to me and say, could you add this additional parameter to the code because I want it to move in this direction, I want it to do this. Instead, I'm providing you with such basic structures that not only are they easily testable, but you can use them in whatever fashion that you want. So that's the Generator Showcase Showdown. Hopefully we'll be able to do a little bit of live coding before the lightning talks to give away some of the O'Reilly books. But I hope you enjoyed that, and my name is James Powell.